So today we're going to start section 2.6, which is looking at a very important connection between continuity of a function and differentiability, meaning we can find its derivative. Now before we get started really looking at the content of this section, let's just review the definitions of continuity. We had talked about the limit definition of continuity was the limit as x approaches a of some function should equal the value of the function at that point. And this definition will solve all of the requirements for continuity. So that's our working definition for continuity today. And then for the definitions of differentiability, I think it's important to write it twice. What we're looking at here, again, the idea of differentiability, most importantly, we're talking about a rate of change, specifically at an instant. So in other words, if we have some just random graph that I'm just going to draw here, just some curve here, if I was looking to find the slope, right, which is the rate of change at a certain instant at this point here, let's just call it A, and then I'm wondering what is there's some output at A, and I'm wondering about the rate of change at that point specifically. So what we had talked about in class was, first of all, looking at a rate of change, it's easiest to first start with a secant line and say, well, if we approximate the rate of change with the secant line, so looking at two outputs, f of x somewhere here, and then f of a, what is going to happen as we slide those 2 points closer and closer and closer together? So as this point here, we'll get closer and closer to that point there. That's how we estimate our derivative. So the definition using limits then, because we're getting closer and closer and closer, we want these 2 points to be on top of each other. So we have 2 points. There are 2 definitions of our limit that we're going to use both today. So it's comfortable just going back and forth between the two. So one definition is we're looking for the limit as that second point with input x is getting closer and closer to the point that we're trying to find the derivative at a. So we're looking, again, the limit implies as those are getting closer and closer. So we look at the output of f of x and compare it to the output at f of a, and then divide by the change between x and a. And again, the limit is implying as these two are getting closer and closer and closer and closer and closer together, essentially so they're on top of each other. So again, it's important to see this definition. And why I write it like this is we see that these two inputs are getting closer and closer and closer together. So the slopes of 2 points, which is our secant, get really close to form our tangent line. So that's our first definition of a limit. Now another definition of the limit that's important that we'll use today is the difference between those points, so the distance between x and a. Sometimes we can just call that distance h, because we're really looking for the derivative of a point. So let's say we're looking for the derivative at some point on our function f of x. We can just use h to signify the distance between those 2 points. So we'll be looking at the difference between our original input and some small distance we increased it. And then here, as we're implying that x and a, those 2 points are getting closer and closer together, the distance between those 2 points can just be called h. So we can simplify the formula and use an h instead of x going closer to a. So I'll be using both definitions of the limit today. So just make sure you're kind of fluent between the both. Now one quick note about this limit definition is that it is making an implication that we know that if this limit does exist, in other words, if we're saying that like we can calculate this here has an answer, well, we're implying that if that limit exists, then it exists from the left and the right, and that's important to keep as in our assumption because we'll use that today when we go through some algebraic proofs. So for example, if we just have some function, I'm just going to draw a random function here. I'm going to draw it in red. Nice continuous function. And if we're looking to find the derivative at this point a, right there, well, what we're saying is we should be able to find the limit as some other point approaches it, right? Because we're using 2 points on a graph. Maybe it's that one, which I'll call, well, I'll just leave it there. It could be that one. Or maybe we're using that one right there. But the idea is we're approximating the slope at this point right here by using a secant line and then getting that closer and closer to the tangent line. So the idea is, it doesn't matter what point I start at. If I were to take this green point, the lower point here, which is to the left of our input, the slope that I get from this point here as I move it closer and closer to that one should be approximating the same slope as if I started on this side of it and moved this point closer and closer to that one. So we're just going to rewrite our limit, making sure that we understand the left-handed limit and the right-handed limit have to be the same. So in other words, what we're saying here, our limit definition of the derivative can be broken down into another statement. We're saying that the limit, as our point on the left side, right, approaching it from the negative side of A, so the limit we'd approximate here as these 2 points get closer and closer together. But again, we're coming from the left side. So the secant lines that are approximating the tangent from the left should really be giving us the same number as if we approached it from the right side. And on the right side, what we're saying then is the limit, as some input we choose got closer to A, but from the positive side, right? And again, we're just copying the rest of the limit. So as these 2 points get closer and closer together on the right side, they should equal the exact same thing we would get on the left side. So we will be kind of using this fact today a lot to help us prove some stuff. So it's just important to understand the connection between these two definitions. So we have some basic definitions out of the way. This is kind of starting to really get into the differentiability of a function, which is section 2.6. So we're looking to see if something is differentiable, right? And just by the definition of that, can we find the derivative? So there's going to be some clear-cut times when we cannot find the derivative. And specifically, we're just talking about at one point of that graph. So it's really important that we're talking about a point of non-differentiability, not an entire function. So we're just going to start with some intuitions on a graph, so then when we see those on a graph, we'd be able to recognize them as something to look for, and we'd be able to back that up with our algebra, which is the ultimate proof. So there's a few classic examples of functions or characteristics of functions that will not be able to be differentiable at that point. So when a function is discontinuous at a point, we won't be able to find its derivative. So like, I'm just drawing a random function here, open and close circle, and let's say this point here was point A. So f of x is not continuous at A, so we will not be able to find its derivative at A either. Another important example to recognize on a graph is a sharp corner, sometimes called a cusp. So I'll just draw two different graphs that exemplify both of them. The first classic example is just your absolute value. It comes to a V, not a U, which I'm trying to emphasize as a rounded corner. So anytime we have a sharp turn like a corner, it will not be differentiable. Sometimes you might see that as a cusp, what we call, which is kind of like a curve coming down into a tight corner. Almost looks like one of those little birds you draw on the horizon. But again, existence of sharp corners. So like here at this point right there at A equals 0 on both of these graphs, we would not be able to find the derivative at just that point. Now we might be able to find the derivatives maybe here at this point, here at this point. We're talking about certain points where we can't find the derivative. The last example, we know that the derivative by definition is us approximating, well, actually finding the slope of a tangent line at a point. So if I have a function, and if I look right here at A equals 0 again, kind of right in the middle, if I had to approximate that tangent line, it looks like I'd have to draw it in vertically in order for it to only touch at one point. Maybe compared to like the tangent line over here, which I can see has a slope. So if we look and we see a graph where the tangent might be a vertical line, that's another clue to us that we should look at that point as a point of non-differentiability. So we're looking at the connection between continuity and differentiability here. And we're going to start with, well, if I have a function that's continuous, I would assume that I'd be able to find the derivative then. But we're going to look at those relationships. First of all, with the classic example of just y equals the absolute value of x, or like f of x is the absolute value of x. Now this function is continuous, right? And we're specifically going to look at x equals 0. So we can obviously see why we'd start with this graph. We know how it is shaped, and on the last example we said that V shape is a very classic shape to look for a point of non-differentiability. So let's kind of prove why now. So we've seen it on the graph, now we can prove it with our algebra. So first we're just going to look at, this is continuous at that point, so we're looking specifically at x is equal to 0. So the way that I'm going to prove this one, I'm just going to use the limit definition really quick and put a table down. So what we're saying here is that the limit as x goes to 0 of this absolute value function does exist, right? And we're wondering if that would actually equal the value at that point. This is our definition of continuity that we went through at the beginning of this video. And if I just make a quick little sketch here of a table, and if I'm wondering what's happening around 0. Now I can substitute 0, and I know that if I substitute 0, the function's value at that point is 0. So I have established that f of 0 it exists. Now I'm wondering if the limit is going to approach that too. So I have to look really close on both sides of it, the positive and the negative side. So numbers that are really, really close to it. So I'm going to just do 2 of them on each side, the negatives and the positives. And if I were to plug these in to the function, I'd see that the output here is 0.01, the output here is 0.0001, same thing here, the output is 0.01, the output here is 0.0001. So I can clearly tell if I'm coming from the negative side or if I'm coming from the positive side, these values are clearly approaching the value of 0. So we've proved that this is continuous. So now that we've proved that our function is continuous at the point a equals 0, or that input of 0, we can prove though that it's not differentiable at that point. As we saw on the graph, there's a v there, so why does that v therefore signify that it's non-differentiable? So we should be able to go back to the definition of a derivative and use that to say why not. So I've copied the 2 limit definitions of the derivatives that we saw at the beginning of the video, and specifically right now I'm going to use this one, because what we're looking at again is we have 2 points. A is 0, that's the one we're focused on, and we're going to use some other point on the graph, some other input called x. We don't really know where that x is, but what we're saying here is this point right here is a equals 0, so we're going to use some other points. We're just going to call those inputs x, so like here, and we're going to estimate the tangent line between the secant line between those as we move this x closer and closer and closer to that point. What we also have to do though is we want to use a second point to estimate it on the other side, right? So this other value over here. What would happen if we looked at the secant between these 2 lines and then got that closer and closer and closer? So in other words, the limit has to exist from both sides. So the secant approximation from this side, so as we got these closer and closer, what would that tell us? It should be the same thing as we get over here. So we'd write that out. What we're saying is, and here I'm going to start again writing out using the definition here, but we know that our a value is equal to 0, so I'm going to substitute that in. So the limit as our second points that we're using, like I put one x in green and one x in blue, as that point is getting closer and closer to our a value of 0. So the inputs that we're moving, we don't know what their outputs is because they're moving. We do know that we're comparing it to our a value of 0. And then we put that over x minus 0. So as this distance between those two gets closer and closer and closer together. So this means the limit from the left side, though, has to equal the limit on the right side. So the limit, as our second point was approaching 0 from the left side, should be the same thing as if we did it from the right side. So as the limit, as our secant from the right side essentially made the tangent line, so got closer and closer at point A, what would this tell us the derivative would be? And let's compare those 2 values. So just continue on work, doing a little simplification. We know what 0 is, that's really easy. So here we're looking at the limit as x is going to 0 from the negative side of just f of x, because f of 0, the absolute value of 0, is just 0. So I'm going to simplify that away, and then on the bottom, same thing, x minus 0 is just x. On the other side of our limit here, we'll kind of do the same thing. We know the absolute value of 0 is just 0, so I'm going to simplify that away. So we have the limit as x goes to 0 from the positive side of just f of x over x. Now what's really important to note here is that for our function, the absolute value of x, we can define that a little more specifically like as a piecewise function. So the absolute value of x is just going to be the value of x anytime the x is greater than or equal to 0. So if I put in 4 into the absolute value, it's just going to be 4 on the way back. If I put in 7 into the absolute value, my x was 7 and I got 7 back. So the input I choose is actually just what I get back. But if I plug in a negative number, so for any x that is less than 0, the output is actually the opposite of whatever I put in. So if I put in -7, the output is the opposite of that, which is just +7. That'll help us rewrite these limits here. So if I rewrite the left side, now the limit as x is going to 0 from the negative side, that means we're using negative x values. So instead of f of x, we know that anytime we put in a negative x value into that function, our output is just going to be the opposite of whatever we put back in. So I replaced f of x with negative x, and we still have the denominator of x. Now this will simplify very easily. This is just -1. Let's go look at what happens on the right side then. Now the right side, we're looking at the positive values of x because we're getting closer to 0 from the positive side. So by our piecewise definition of our absolute value function, instead of writing f of x, we know that if we're on the positive side of our x values here, which is what our limit is, if we're in the positives, the absolute value of x is really just going to be x itself. And again, just from the original definition, or the original thing we wrote up here, we have to divide that by x. So x over x is clearly equal to 1. So we can see right here that the left-handed limits and the right-handed limits are not the same. Here we input. So that's our very first super important thing we just proved. Just because a function is continuous at a point, so continuity at a point, does not prove that it's differentiable at that point. Because we just showed that our function, the absolute value of x, well, it is continuous at 0. It was not differentiable because this didn't exist. We couldn't find the limit of this function, and since this limit didn't exist, the function was not differentiable. So let's take a look at another example, maybe something that's a little less comfortable to us than the absolute value. So I have this other function, x to the 1/3 power. Now I have gone and just included some graphs really quickly that I just pulled off the internet. So the basic graph is right here. We always want to start by looking at that graph just so we can kind of get a feel of the function and where we should be looking at for special points that aren't actually differentiable. But we can see from this graph, and I'm not going to prove it necessarily, but we can clearly see from this graph that it is continuous. So continuity, yes. And it does look like it's continuous like a lot of places. What I included down on the second graph though, so down here, was I just zoomed in a little bit. You can tell from here, but I took this little part and zoomed in. And what I'm looking at here specifically at x equals 0, if I was going to try to draw a tangent line to that, meaning a point that only touched it just once, we would see that that tangent line is actually way closer to vertical than anything. So I'm going to draw that in with a black line, if I can here. So if I looked at the tangent right here, that line is essentially vertical. So I have some sort of kind of intuition that at the point 0, something is going on there. It's continuous at that point, but I don't think it's differentiable because I saw the vertical tangent line. So that's my clue to go prove it. So how do we prove that it's not continuous there? Well, again, we're just going to use that limit definition. And I'm going to use the limit definition that uses h this time, just so we can see a different version. So if it's differentiable at the input of 0, this limit, right, which is the derivative limit, should exist. So we're going to go ahead and plug some things in. So we know that we're at the point where x is equal to 0. So I'm just going to substitute those into my limit formula. So we have the limit as the distance between our two secant points used to estimate the tangent is getting closer to nothing. We would have, well, if x is 0, that's just f of h minus f of 0 over h, which again is just the limit. As the distance between our 2 points is nothing, we just have f of h over h. So continuing the work here, we know what f of h is. So we're looking at the limit as h goes to 0. So f of h is just h to the 1/3 power over h. I'm going to rewrite that one more time using the properties of exponents. This would be the limit as h goes to 0 of 1 over h to the 2/3. So what would this limit be then? This limit is actually interesting, right? What would happen as h is getting closer and closer and closer to 0? Let's do some quick evaluations, right? So what happens if like h was a really small number? Let's start with 0.01. We would get 1 over 0.01 to the 2/3 power, which I calculated to be about 21.54. If I make h even smaller though, so in other words, those 2 points used to estimate our tangent are getting even closer together. So the distance between them is even smaller, so 1 over 0.001 to the 2/3. I calculated that to be like 100, I think. And just one more for emphasis. If I looked at, well, let's make those points even closer. So let's make the distance between them, h, even smaller. So we look at the limit definition, 0.0001 to the 2/3. I calculated that to be about 464. So why do we care? What we're looking at here is as we take our points or our h value, the distance between them, and they get closer and closer together, right? In other words, our h values here are getting closer and closer to 0. What's happening to our outputs? Well, they're definitely not growing to a certain point. It looks like they're just growing without bound, right? This was at 21, then it's at 100, then it's at 464. So in other words, the slope of that tangent is just increasing and increasing and increasing. If I got even closer and closer and closer, that value would just get higher and higher and higher. So this limit, we don't know what it's equal to. This limit does not exist because we can't say that those numbers are converging to a certain point, like the slope is 7 or the slope is 12. So since that limit did not exist, we can say that our function is continuous at x equals 0, but it is not differentiable. So in other words, if we try to find the derivative at 0, we couldn't. So this is our big theorem for today then. What we're saying, what we're going to prove, if we know that continuity doesn't prove differentiability, but what about the reverse? What if something is differentiable at a point? Is it going to be continuous? So our theorem that we're going to prove, if a function is differentiable at a point, then it is also continuous at that point. So we're just looking at the reverse. So to start our proof, we have to start by saying that f of x is differentiable. So we're going to assume that we have some function that is differentiable at a point. So I'm just going to draw a random function. Let's make it look like this. And we're saying that it is differentiable at this point a. So it has some output there, f of a. Just compare that. So what we're going to look at then is if we know the derivative exists at that point, can we also then assume that the way I drew the graph is correct? Meaning, is it a continuous smooth curve at that point as well? So we want to prove continuity. So what we're going to need for continuity, I'm going to introduce this other point. So I'm just going to look at some other input value. I'm just going to call it x. And x, of course, will have some output value of the function, maybe like right there. So again, we know that it's differentiable at that point, but we want to prove that it's continuous. And what I want you to think about here is we know this idea of continuity is smooth and connected. So I'm asking you, what would happen if I took this little second input here? I'm just going to use this circle to kind of signify that. So if it starts here, this little input, if something is really continuous, what would we expect to happen as these 2 points got closer and closer together? Well, if it really is continuous, I would expect those 2 points, as I moved them closer and closer together, to be the same value, right? Compared to something like this, if something really was discontinuous at a point, if I started with 2 points, maybe like right there, and if I said, well, where's this other point going to go? So again, I'm grabbing this other point that I'm moving. If it was discontinuous, I would expect there to be some sort of gap in between them on the y-axis. Compared to over here, if something really is continuous, if I took this second point and I moved it closer and closer to the first point, they're going to be on top of each other. In other words, what I'm saying is if something really is continuous, I would expect the difference between those 2 points to be 0 because they're right on top of each other. Compared to over here, if it wasn't continuous, the distance between my 2 points would not be 0. Right? There's some sort of difference in between them right here. Maybe it's 1, maybe it's 2, maybe it's 3. So what we're assuming then is we think that if something is going to be continuous, the value of those 2 outputs as they get closer and closer together, that should be 0. The difference between them should be nothing. They should have the same value. So right there, I'm using the language that signifies a limit. I'm trying to take this second point right here and make it closer and closer and closer to something else. So closer and closer and closer. That's the definition of a limit. So I want to know, as the point f of x and f of a get closer and closer and closer together, what is going to happen? So in other words, as the limit, as these 2 inputs get closer and closer together, what would happen to the difference in their outputs? And again, I'm expecting it to be 0, because if it is 0, then we're signifying again that that second point that we're drawing right here, as it gets closer and closer to that one, it will be that same value. So we're hoping to see that it's 0. So now we're just going to manipulate it. Since this is a value, I can algebraically manipulate it. So I'm going to multiply it by a special form of 1, which is x minus a over x minus a. Again, if I multiply something by 1, it won't change the value of it. What I'm going to do then is I'm just going to get tricky how I rewrite something. So I've introduced a product now, right? Because I decided to multiply it by 1. So I'm going to use the product limit, or property of limits. So the limit of the product is the product of the limits. So as x goes to a of x minus a. And then I'm going to choose to rewrite the second one a little tricky here. The limit as x goes to a of f of x minus f of a all over x minus a. So again, what I did is I just broke up this fraction as x minus a, and then the bottom is 1 over x minus a. So I just rewrote where I wanted to multiply it. So you can see that if I were to go ahead and multiply these 2 original functions back together, this one and this one, I would get back to my original statement. Now, why did I do that? Well, we can start to evaluate some stuff here. So the limit as x goes to a right here, this is clearly going to be 0, because x minus a is going to be 0. What we're looking at over here now, though, the way that I wrote this, is the limit definition of our derivative. And again, if you need to go back to the first slide where we introduced that, that's the exact definition. So this right here is the definition of the derivative at point A. So in other words, we're looking, if the limit up here is 0 times our derivative, that's just 0. Now, this is important. We know this exists. We know not every function is differentiable at every point, but here we know that this value a does have a derivative because we assumed it at the beginning. So why do we care about this point, like the value is 0 though? Well, that does confirm what we thought. we originally thought that if something was continuous, the limit of these two differences, so as these 2 points got closer and closer together, that difference should have been 0, and we just proved that it was. So we proved our intuition was correct. Now, why do we care though? So what we're saying is if we start with our original thing, so now we know that this limit, as these 2 points get closer and closer together, in other words, we think they should be on top of each other, they do get on top of each other. So now we have an equation that we can just manipulate. So I'm going to add f of a to both sides. So in other words, the limit as x approaches a of f of x should equal f of a. Because I'm just manipulating this equation by adding f of a, which is just a number, to both sides. So this is the definition of continuity from the beginning slide. So we have just proved that if something is differentiable at a point, then it is continuous at that point. So one quick example of why we care if something is differentiable that is continuous, it saves a lot of time and a lot of shortcuts, right? So like example number 4 says that, show that the function f of x equals x squared is continuous everywhere. And what they're implying then, everywhere, is at all a values. Or in other words, for all values of a which belong to the real numbers. So if you haven't seen this epsilon notation, this means belongs to, which would be impossible to prove by every value. There's an infinite number of a values, so we can't just go ahead and test 0 and 1 and 2 and 3. There's got to be a way to prove it all at once. So what we do know is that if something is differentiable, then if we can prove it's differentiable, by default, it will be continuous. So I'm going to try to prove that this is differentiable, because if I can say that the function is differentiable for every single a value, then by default, it's also continuous. So if something is differentiable, that means for any a, doesn't matter what a value you choose, I can find this limit. So the derivative of a would be given by this limit, the limit as x goes to a of f of x minus f of a all over x minus a. So just continuing with manipulation of that limit, I'm going to evaluate the functions. So we're going to rewrite this now. So f of x, so in other words, we're looking for the limit as x goes to 0. Now f of x is just x squared. If I plugged in a into the function, I would get a squared. And that's x minus a on the bottom. I'm just going to factor x minus a, x plus a, all over x minus a, and we can see that this cancels. So we would get this, the limit, that's an a, sorry, as x goes to a, is really just x plus a, which we know if we plugged in a, we can directly substitute a, which would just be a plus a, which is 2a. So in summary, what we said, no matter what value of the input for our function you choose, any single a value you want, the derivative of that function will just be given by 2a, meaning the derivative at any single point will exist. And to find its value, I just use this formula. So since f of x is differentiable for all a values that are real numbers, then f of x is continuous for all of those same values. Last example in the video today, just kind of a classic problem that you'd encounter. Decide if this function is differentiable at the point x equals 0. So I did include a graph just to kind of get a basis for what I think. And when I look at the point x equals 0 right here, I think it should be. Like, I don't see any points, I don't see any cusps, I don't see discontinuities, and I do see a horizontal tangent line, but not a vertical one. So I do think it is differentiable at 0, so I'm backing up my intuition now with my algebra, so we should be able to prove that it is differentiable at 0. So in other words, the limit has to exist at 0. So if we try to find the limit, so here's our limit definition of the derivative. So now just continuing to rewrite, I'm going to substitute the x value that we're looking at, which is 0. So this would be f of 0 plus h minus f of 0 over h. So now let's substitute that into the actual function itself. So we're looking for the limit as h goes to 0 of f of h minus f of 0 all over h. So one more time, the limit as h goes to 0. So now I'm plugging in h. This is going to be h times the absolute value of h minus, now if I plug in 0, the 0 times anything is going to be 0. So that's just going to be minus 0 over h. And then I can clearly see here that the h's will cancel. So my limit at the end, I can simplify to the limit as h is going to 0 of the absolute value of h. Now here I know that if I kind of look at what's going to happen really close to 0, the absolute value is going to approach 0. So I did prove that yes, this was differentiable because the limit definition of our derivative existed.